So just being able to look at just solving with exponents, we want to be able to adapt and use our properties, use the negative exponent, being able to distribute that the negative exponent or the exponent. What I would first do here is I would first just bring down my term 3ab squared c. There's nothing really to that problem that we need to really do. So I'm just going to bring it down. The next part of it, or our next term with the parentheses, is I'm going to go ahead and get rid of that negative. Okay, you could distribute it if you did that, that's fine. You probably did it that way as well, just like you did for the do now. But I'm going to go ahead and just flip my terms first before I distribute. So this is going to be everything on the bottom goes on the top. So there, here, and here. So I still have that squared. All I got rid of was the negative value for this. What I want to be able to do now is I'm going to go and distribute. Oh, what did I do? What did I do? Oh, there it is. I'm going to go and distribute. So I'm going to distribute this 2 into every single term on the top and bottom. This is going to be 3ab squared c. And then I'm going to get c to the 6. 2 squared will just be 4, so I'm going to reduce down just quickly on that. 4b squared. I'm going to bring this to the top for you guys over here. I'm going to multiply everything across first before I reduce down. So this is 3ab squared c to the 7th, just by doing my portion right here. All over my bottom portion, which happens to be 4a to the 4th b squared. When we simplify out, our 3/4 are going to remain the same. Can't reduce that one out. My a terms, I have 1a on top, 4 a's on the bottom. So I'm just going to eliminate one of the 3's, or one of the a's, sorry. Ugh. This will just be a to the 3rd. My b's is going to be b squared on top, b squared on bottom. They're the same, so essentially we can just cancel them out. And my last term, c to the 7th, remains c to the 7th. Did we get that? Yeah? Yes, sir. Essentially what we do. The a on the bottom to this, I see what you're getting at, right? Because you got a, you could have written it like this. You probably wrote it as 3/4 a to the negative 3 c7. Well, what can we do with this? Change it back into the fraction on the bottom. So either way would have worked for me, right? If you would have reduced it so that I had no fractions or no variables in the denominator. Yeah, so it goes vice versa. Does that make sense? So I see what you did there. That's pretty good. That's good, right? So we can rewrite it. So what you did is you subtracted them, and you got this answer. And then all I did is I just did the extra step and just put it down below. So I have no negative exponents. And I think that's what it's going to say tomorrow. Put have no exponents in your answer, right? If I don't give you that option, you can have it either or, right? So usually in math, or at least for my professors, prefer not having negative exponents. So we always just, if it was on the bottom or top, we just switch them. So you always have positive exponents. But it's up to you. It's up to you. Okay. The next one here we have below. What I want to be able to do here first is I'm going to go ahead and reduce down as much as I can, at least for our first pair here. My c to the 4th and the c, just basically take away one c. So I'm going to get c to the 3rd up on top. My d's here, d to the 3rd. Basically, I could take 2 d's away from it, leaving me just d on top. I'm going to leave this over 1 now because there's really nothing there. I want to go and distribute the second term over, so I'm going to distribute that 3 to the 2, the 3 to the 3. So I'm going to get d to the 6, c to the 9th. We're going to go ahead and combine our terms across first before I do anything. C to the 3rd, d to the 7th, all over my bottom portion, which is going to be just c to the 9th. I'm going to show it your way as well. So this is probably the way that you did it because we're dividing, right? So we could have done our c's first here. And what he was essentially saying is we're doing c to the 3rd minus 9 because of the same base and we're subtracting them. And then I'm just going to rewrite my d to the 7th. So this is another way you can do it. If you prefer me doing this, let me know. I have no problem doing this. 3 minus 9 is going to be negative 6, d to the 7th. And then that negative 6 would be what? On the bottom, right? So we have this one. C to the 6, sorry. Got too ahead of myself. Thank you. Boom. Either one would probably work for me. I probably won't even tell you negatives. If you put them in both forms, I'm okay with that. One is no negatives, one's is simplest form. Yes. Uh-huh. That's fine. That's fine. When you get into pre-calculus, there's a lot of ways to get the same answer, right? I could have done it a multitude of ways, right? I could have distributed, especially for the first one, I could have distributed this negative, combined all my terms first and then reduced down. I flipped it, then did the distributive. There's a lot of ways you can do this problem. So I'm not going to lead to like, oh, you didn't do my way. Oh. I'm not that kind of a teacher. As long as you're able to do a logical progression. In college, I had proven that my professor used a whole board for a proof, because I took proofs, and I did it mine in half the steps. And he was like, well, this is not. Whoa. Oh, you found a fast way? I'm like, yeah. Okay. Yeah. All right. So I'm not going to be too heavy on that. As long as you find the logical way to go through the material, by all means, please go for it. Okay. Here we go. Exponents and radicals is what you have on your paper. I try to condense it down. You're going to have to write some stuff on the backside with this. As you can tell, for the radical portions of these, there's not that many problems we're going to go over. This is kind of tricky. I think out of a lot of what we see from pre-calculus and integrated 3 is being able to understand. On there, right there, boom. Got you some extra. It is kind of important that we're able to see these radical forms of these. So kind of bear with me. If you want me to stop or slow down, that's why I didn't get through the other classes as well. We're going to just cover the harder problems tomorrow. We'll go over them before we do the quiz. I think for tomorrow's quiz, what I'm going to have is some interval notation. So being able to convert from the brackets and parentheses, graph inequality and interval. We'll do a couple of those. And then I'll give you a couple of exponential problems, the ones that we just did, like 1 and 2, the practice ones. And then I'll probably do a little bit of the radicals, and that'll be it. So it shouldn't take us that long. I'm thinking maybe 1, 2, 3, maybe 5 or 6 problems for your first quiz. We'll do it. We'll grade it in class, pass it back. We're done for the day. I don't try to have stuff on Friday. Again, no homework on Friday. But no. I don't even want to get good on Friday. Okay, so here we go. First part of this, symbol means positive root of. Positive root of. A lot of what we're looking at is perfect roots on a lot of these, so being able to kind of simplify down as best we can. One thing that I kind of want to go over, and I wish you guys can kind of put that in on the side, I think you guys have room on the side of you, is to note that the following, that another way for the square root symbol to be, another equivalency for, like, let's say the square root of a, these are synonymous with each other. The second root of a. That part in front of it basically means that we have a value that represents you know, what two numbers, I always think of it as what two numbers will give you the A value, right? Another way we can write this, and what is kind of shown here, is what number squared will give you A. And I know there was a lot of confusion, especially when we converted from exponential to logarithm, right? I don't know if your teacher taught you guys that last year. I know these are not logs, but being able to convert back and forth between them is going to be helpful. Just being able to identify those as well. So just kind of keep that in mind as we do these and go forth. Okay. With these ones, our definition of the nth root, okay, is we want to be able to find a value in which will give us our solutions, okay? I always look at it as what numbers can be multiplied 4 times to give you 81. I like to write them a little bit differently just because I'm a visual guy and exponents are a little bit easier. What I would do with this first one here is I would convert this to what number can be converted to the 4th power to give you 81. What do we got? 3. Okay, 3. So your solution to the 4th root of 81 is just 3. Okay, I'm hoping that kind of helps you out. That makes a little bit more sense. Be the same thing here. What would be a number that when you raise it to the 5th root gives you 32? 2. We're going to get rid of this last one. I'm not going to cover that until later. This one's a little bit more trickier than I'd hoped. We're not going to go over that. I'm going to tell you guys that one. Okay. Essentially, again, we're going to do the same thing. What can we convert this to raise to the 3rd power to give us -8? -2. So whenever we have it raised to a different power, mostly negative numbers, we can have both positive and negatives for these. So just keep that aware. Keep that aware for these. We're going to kind of follow through. Cool beans? Cool. Now here we go. Properties of our roots. Properties of our roots. Okay. Number 5, if you guys can, just kind of circle it. You don't really see that many differences between 5 and 4. So 4 is going to kind of be it's an even or odd type. Can strictly be positive. We're not going to focus up on that. Don't really worry about that. Now, the properties that we see here, 1 through 4, are going to come up a lot, especially when we start solving out and using a substitution method or being able to just identify the root powers of fractional exponents all the way from the 3rd root. But whenever we get this on top, the first property tells me that if we have 2 variables within a root of a number, they can be separated. We can separate them as 3 to the square root of -8 times 3 times the square root of 27. We can do this if they're underneath the same root. Okay, if they're separated and they're different, we cannot do that. The root of -8 is going to be -2. The cube root of 27 is going to be 3. So our solution is going to be 6. So we definitely want to be able to see these. So we should have reviewed them last year. You guys should be able to review them. If we're given another type, so this second property tells me that it's a ratio inside of a root number, we can separate them as well because they're underneath the same root. Exactly what we're going to do will be the 4th root of 16 over the 4th root of 81. 4th root of 16, 2. 4th root of 81, 3. Next one tells me that if I'm taking the nth root of another root, we can essentially pull out both roots and multiply together on the outside. Okay, so if you're taking a root within a root, you can definitely do that. I'm going to change this up so you guys can see it, like what number is in front of there if we don't have any value. 2, right? We can always write it as 2. This is why it kind of goes back to what I just said, just so you have some kind of visual representation. Right? So these two are exactly the same. A square root of the third root, so we can just say a squared or 2. We can pull that front value out, those 2 root values in to give you 6. Root 729. What is the root of 729? 3. Okay, so hopefully that's going to help you guys out. The last one that we're going to get here is if we're taking the roots, the same root power, raising it within the same root, or sorry, taking the root, raising it to the same exponential will give us the same value. In this case, we're just going to get the same value of -5. Okay. If it's odd, we're going to get the same value. If it's even, which is the bottom one, which you're going to see, I don't know how often, we're just going to say it's going to be the absolute value of -3, +3. Absolutely. Yeah. Kind of counterintuitive, but I'm not going to spend that much time on it. We got bigger fish to fry. Okay, so we're going to look at those type of properties. So here we go. We also want to look at how to apply some of these. So simplifying expressions using the nth root, or root. So the first two are going to kind of straightforward. Now, I know we did this last year. This was kind of crazy. Not crazy, but we kind of did a lot of these with your integrated 3 teachers. And there was a lot of confusion between some of you guys doing this. What I used to tell my kids is write out all the roots of that specific type of root. What I mean by this is the following. Let's say we have a square root. We want to be able to write out all the perfect roots of these. So if I'm just going to write up on top so you guys can see them, we have 1, 4, 9, 16, 25, 36. What's next? 49, 64. I'm going to tell you right now. I'm basically finding the perfect roots. I'm basically using, these are all perfect roots. What's the square root of 100? All the way down. And what I want to be able to do is I want to be able to find that specifically for my symbols of what we have to reduce down. Okay. Now, with this, we want to be able to use the largest number we can make to form 12. So choose the largest value you can think of to make the value 12. So what 2 numbers can be multiplied together to give you 12? 4 and 3. So because we have that, we can split it, square root of 4 times the square root of 3. And because we have the property in which if we have 2 numbers within a root, we can separate them. So we can do the square root of 4, square root of 3, and simplify it to 2 root 3. Does that make sense? Because I know when we did this last year, a lot of you guys got confused on doing this, right? I did get to you. So I'm hoping this is going to kind of help. Okay? And we want to be able to choose the largest value. Okay, I'm going to show you the reason why this is going to be a little bit more trickier for the 7. Okay? Because what's the first one you think of when you think of 9? When you think of 7? 72. 9 and 8. 9 and 8. But what would be a better number to use for 72? 36 and 2. Now I'm going to show you a reason why both will still work, but one's a lot faster. Okay? We're going to do the quick one, or we're going to do the long one first. Someone told me 9 times 8, right? Perfectly good answer. Let's see. It's a root in here. We can definitely use that. So let's see what happens. If I do it one way, I'm going to show you one way. So we can split this up into the square root of 9 times the square root of 8. So it's going to be separated, square root of 9 times the square root of 8. We're still going to get 3 root 8. Okay? Technically, it's right, but can we reduce it down further? Right? Because 8 can be reduced down further, right? what would be the two numbers that can be multiplied? So 4 and 2. So we're going to get the square root of 4 times 2, 3 root 4. I know I'm doing a long way. I just want to show you. 3 times 2 root 2 or 6 root 2. This is a long way. I know some of you guys can still do that faster, and that's fine. But this is just a long, cumbersome way. You got to think of doing it twice. We essentially have it once here, and then we got to do it again here. But if we choose the largest values in here, it becomes really simple because the roots of it goes away. If I do it the other way, in which we chose 36 and 2, check it out. If we do square root of 36 times 2, this becomes square root of 36 times root 2, 6 root 2, done. Does that make sense? So just try to find the biggest number that goes into 72. Okay? That will help you out. Okay, that will help you out. Okay? So that's why we want to be able to just to choose our value, the largest root value in here. Now, the next one that we're going to do here, so I'm going to leave that one for this. So now, these are perfect squares. We want to look at perfect cube roots. So I'm going to go ahead and just write them out. You don't have to go that big because they're kind of big numbers. They go up really fast. So if I'm just going to write those down, we have 1, 2 times 2 times 2 would be 8, then 27, then 64. 5 would be what? So it jumps up fairly fast. So the perfect roots of these are going to be looking bigger. Now again, do the same kind of process. What's the biggest number from these that we can make out of 40? 8 times 5. So we're going to do cube root of 8 times 5, which will equal the cube root of 8 times the cube root of 5. Cube root of 8 is what? 2. So it's going to be 2 cube root of 5. Done. Does that help you guys out? Is that easier to do than freaking you guys out a little bit more? I don't know why teachers do it harder way, man. Don't do that. Messing kids up. So that's a good way of doing it. It's a really good way of doing it. You know, if we had a fourth root, we would find all the perfect 4s, which that goes up even faster. It goes 1, 32, what's 4 is 16, 62, 56, I want to say. So it jumps up fast. So more so likely we'll see more of these type of problems. Or it's a perfect root of 3, the perfect cubes of squares. Then we'll look at them as we go along. Okay. Here we go. Looking at these next ones. So simplifying the expression involving the nth root. We're going to look at the nth root involving some of these. So now we're just looking at practice problems. I just want to try to get into them and just start up. These are more simpler problems. The more that we do, and we'll see them tomorrow, we're going to do the harder ones. And we're going to deal with fractional exponents and how to do that. For the first one over here, we have them underneath the same square root. So they're square roots of each other. So just because they're separated doesn't mean they're automatically separated. What can we do with those two? Put them together. So that's exactly what we want to be able to see here. So just because we go one way, we can actually go the opposite way and condense them into the same form. Sometimes it's easier to separate them and to solve them. Sometimes it's easier to put them together and solve them. It kind of just really depends. Okay, square root of 100. Can I write this? Plus or minus 10, right? Whenever we take the square root of a value, it's always going to be plus or minus that value. Okay. Would I be mad that you just wrote 10? No. But if you do future stuff, I'll make sure that when we go over that material, that we took the square root, we've got to make sure that we have 2 separate answers. Especially when we do conics and we go over where they lie on the x and y axis, we've got to make sure that we have that correctly done. Yeah. As of right now, we're just going to note on it. We're just going to note. I'm okay with just leaving it as 10. So I'm not going to be too picky if you're like, oh, you didn't put plus or minus. No, I'm going to leave it like that. I'm going to leave it like that. When we get into more of the harder stuff, the conic sections, the plus and minus stuff that we really need, that's when I want to hammer it. So as long as you understand that whenever we take the square root, we have plus or minus 10, Keep that in the back of your head. I would have had you guys just know the basic stuff before. Is that cool? Okay, for the next one here, we have them as the same, the fifth root. Okay, the fifth root are the same, so because of the same, we can reduce it down to the same root value. The fifth root of 64 over 2. This is going to look nice because we can get the fifth root of 32, which happens to be 2. So individually, these might look like extremely hard problems, but because we can reduce them down a little bit, it'll be a little bit nicer. So we want to be able to see a lot of these. Okay. We get out 46 today? Okay. Want to make sure I have plenty of time. Looking at these ones. We're looking at these ones. We want to be able to apply different variables to this. And do me a favor and highlight this little one. Highlight A. Or circle it or put a star next to it or put a hint and 3 stars or little rainbows. I don't care. Whatever makes you happy. This is one that kind of confuses kids, but we can also apply it in different ways. The fact is we have a variable that represents our number. What that number is, we don't know, so we can't really determine what a perfect root would be for that, but we can split it up. What I want to be able to see here, and this goes back to the property number 1, I believe, property number 1, where I want to be able to look at a good property and separate them, but it's also going to come back for 4. Okay, it's also going to look like 4. And here's what I mean by that. 1 and 4, 1 and 4. Okay. I want to be able to kind of simplify this out. And it's almost like finding the perfect square roots or the perfect cubes. But the good thing about this is, let me see if you guys can see this. We're going to do the cube root. So we're going to write this in 2 separate ways. The cube root of x to the 3rd times x. I basically split them apart by 1 exponent. Okay? If I were to multiply these two together again, it should be x to the 4th. And they just separate it. And there's a reason why I separated it into x to the 3rd and x, because I have a cube root, right? And now what I look at that is if I separate those by doing that property on number 1, we're going to have a nice value. If I separate these two, we're going to get the cube root of x to the 3rd, which comes back to your property number 4, and this just still is the cube root of x. Does that kind of make sense? This is kind of why I wanted you guys to highlight it. We can still separate them. We can separate our value. That's essentially what we're doing when we're writing out the perfect squares. We're basically separating the 2 numbers into terms that we can reduce down evenly. But we can do that with a cube root or any type of power. So what would be this value here? What would be the perfect root of this? X. It's by itself. Raising it to the same power is essentially x. 3 root x. So just kind of mull that over. I don't know how often we're going to see that, but if I need to cover it again tomorrow, I definitely will. Okay, we separated them. For this one as well, I want to be able to reduce down. So now we're just simplifying. We're using our properties. They're all within the same root power. So I'm going to go ahead and separate each term. My first 81 is here, which kind of is going to look nice. The 4th root of 81 is one of my terms. I'm going to do my x to the 8, 4th root of x to the 8. And then I'm going to do my last term, which is my y to the 4th, 4th root of y to the 4th. I'm hoping you guys can see some of these and how they're going to look. What would be the 2 easy colors to do first? The 81, right? Because we know that value, and even our last one, right? We know that the 4th root of the 4th power. This might be the one that might be tricky, right? Hopefully we can see it. But we're going to convert that into the. So the 4th root of 81 is going to be 3. And then our last term for our y, so the 4th root of y to the 4th power is just going to be y. Okay. Now, with the middle term, I know some of you guys are like, I think I get it. I think I know what to do. I always go back to writing it as an exponential. What raised to the fourth power would give you x to the 8th? Like that. It would be x squared. So this is my value then which I want to use. So I'm going to get 3x squared y. I want to be able to see those different times. Yes. One more time. This is reduce it like this, so separate them. To separate them, yes. You could do that. You could do that. Essentially what you're saying here is we can have done the fourth root x to the 8th here, right? And then separate that into what? X to the 4th, right? So x to the 4th, and then we'd have to do something like that. And then what would happen here is we'd get x to the, we'd separate them. It's just more cumbersome. We would get what? X and x, or they work the same way. Just a little bit longer. I know I showed all the steps, but if that can make sense to you and you still want to do it that way, hey, do it. It's just, when we do something like this, I do something like this, like 50-50. Right? So I just kind of show it the other way of just writing it this 50-50. Easier to see it. Your call. Your call. However you want to do it. Are we good so far? Is anyone like super confused? Do we kind of do it okay? Are you guys just tired because it's Thursday and your first week of school? A little bit of everything? Okay. Here we go. I think we're going to try to end. We're going to end on this. Let's see what we get. Let's see what we get. Maybe do one more problem so you guys get homework. Okay. Combining radicals. So we got two more. Okay. Combining radicals. Now, instead of like adding the 100 or 232, we can't do that. When they're separated by operation, in this case minus and plus, we have to do something different with that, right? So again, break them into smaller chunks. Separate them. Separate them. Can we simplify the square root of 32? Can we simplify the square root of 200? That's what we got to do first before we simplify out. So again, this goes back to having out your values. In this case, your perfect roots, right? Because the roots, so 1, 4, 9, 16, 25, 36, 49, 64, 81. You guys don't have to write this. I know I'm just writing this for you guys. Okay. But we just want to be able to find out. Again, what would be the biggest number I can create to get 32? 16 and 2. So I'm going to write that as 16 and 2. So this would be the square root of 16 times 2. Can I just reduce this down and just go 4 root 2? Are we okay with that? Hopefully you guys can see that. Want to be able to see that there. The next one we want to be able to do is 200. We want to find the biggest number that we can multiply to get 200, which would be what? 102. Loving it. Loving you guys. You guys are doing awesome. 102. Can I just write 10 root 2? Perfect. Now, because they're ending in the same root power, what can we just do with them? Add them directly. Okay? We can just add them directly, so this would be 14 root 2. Another way that people like to see it is if you think about it, we can undistribute the root 2's. We can undistribute, so this is just another way of thinking about it. We can get the root 2 of 4 plus 10, right? Or we can do it the opposite way, just so you guys can see it better visual. We can take out that root 2 in the back, so get 4 plus 10 of root 2. Because if we were to distribute it, it would look like the same thing. Or we would just get 14 root 2. Same thing. However it works with you, I'm okay with that. How are we doing so far? Good. Okay. The next one that I want to see here, again, is getting to more trickier problems. We're looking at a B, third of B, there's nothing we can do with that. We'll figure something out. Again, we have an operation here that separates them. We know they have both B's in them. So I know I think I have to do something with them. When I look at problems like these, I go, let me just look at them piece by piece. So I'm going to try to reduce this one as much as I can. So I'm going to separate them. I'm going to use that property number 1 to separate them. We're going to get square root of 25, square root of B. We're just separating them. I'm still going to drop down that negative. And then, can I separate these two as well, like we just did in the other problem where I had the x to the third? So how would I want to write that out? Square root of B squared, square root of B. So now we're kind of getting something nice here. We're getting nicer values here, right? We're getting nicer values. So let's see what we can do here. Square root of 25. So we're going to get 5 square root of B minus B squared would be, or square root of B squared would be B root B. Are we done? What can we do? Subtract them. How would we write that out? Negative. Hold on. What? Negative? We just have a 5 b with it. All these are terms. So we reduce it. I see what you're trying to do there. Okay. If you want to simplify it more down one more step, just how I did in the other one, it would be 5 minus B times root B. Right? Because if you were to distribute that back in, it would look the same way. But because 5 and B can't be simplified, we just leave it as it is. Does that make sense? If you were to tell me right now, okay, because I'm thinking of a little easier play than other people. If you were to do this and write it as 4B minus B squared or whatever, what we just talked about, I would look back at this and give you credit. Does that make sense? I know the extra step you might have just like freaked out like he's sticking here. He's tricking me because I know I gotta reduce. But I see this, or I see this, I'd be happy. I'll give you credit. Is that cool? So if I ever see that on your guys' paper, hey, you said, let me know. Cool beans? Awesome. We have what, 10 minutes left? 6 minutes, 7 minutes? 5. So copy down those two. We're going to end here, I think. Let me just make sure. Yes. But we got to do perfect roots and stuff like that, but we're going to do those when we get back. I'll finish up everything else. We'll do those times probably before we can do it too. After this point, we're able to get all your homework. So it's okay. I just want to cover that. Hopefully, you guys know how to do this. What's up, brother? So in mathematics, being able to rationalize the denominator means that there's no rational expression on the bottom of it. And what we want to be able to do is essentially get rid of it by doing a manipulation of our root value. No. You don't necessarily call it that. We're going to get up in the answers. Two more. Okay. 3 extra. Now, what we're going to do, these are two separate types of problems, but we're hoping to help us out come up with values. Essentially, what you're getting here on the expression up here is that it's multiplying itself by 1. 1 times anything is itself. And what they're basically converting this 1 into is the same value down below. It's going to give you the same root value. I know these values are different. All we have to do is multiply these two graphs to get a regular value, simplify the one up on top. So if we're doing the one down the bottom, what value would I use to rationalize the denominator? Square root of 3. Essentially, we're going to get up on top is the square root of 3. I'm going to combine these two to get the square root of 9, which will just be the square root of 3. You guys probably did a lot of these last year, especially when we did the unit circle. Remember that? Oh, yeah. Probably did a lot during that. That was a 2 root 2, 3 root 2. Okay. Now, the bottom one is a little bit different because it's not just a root value. You have to look at something different. And I'm going to try to pry your brains out of this one, but I'm hoping you guys are going to see my logic here. This is going to go back to the property number 1. We want to be able to find a number that's going to work with this. What value would you assume that's going to work? What do we assume? What did you say? 25? Why 25? Why would 25 work? Why was 1 over the cube root of 25? I'm sorry. Why would the root of 25 work? Why'd you use 25 and not 5? 5 times 5? Think of it like this. Think about it like this. If we were to use 5 in here, let's say we're to use 5, and we use that property in combining our terms together, I would get the third root of 25. Is that even a perfect cube root? No. Okay, but what would be a perfect cube root using 5? 125. So if I make it 25 and 25, this becomes a square root of 125 on the bottom. So we're trying to find just a perfect root to get rid of it. Right? Does that make sense? No? I'll show you again right now. It should just be 5. Okay. Another example of this, and we're going to finish up on this if I need to go over it again tomorrow, would be like 1 over, let's see, the cube root. I'm trying to think of the number. Of 2. Right? We would assume it to be the cube root of 2 over the cube root of 2. When we multiply it out, we're going to get the cube root of 4. Is this a perfect square? Is this a perfect root? Right, what would be the cube root of 4? It wouldn't work out, right? So what number should I multiply it by to give me a better value? 4. Why 4? Because it would turn into 8. So if we change this to 4, we would get the cube root of 8. And now we're going to be able to reduce down to 2, 3 root 8 type of deal. But still, or sorry, that's fine. I know I can still reduce on the top. Oh no, it's 4. Wrote it down wrong. Does that make sense? Yeah? Yeah. If I need to cover it more, I will. Okay. Good. So all of the problems that are on there, it's like rationalizing the expression. We're going to do more of these complex problems tomorrow if you guys want to check these out. We're going to look at fractional exponents, and then we're going to do a little bit of the trickier ones. So we're going to kind of do some of these harder ones, some that look like this. Simplifying by eliminating the negative exponent, and stuff like that. Okay? You guys have a good day. We'll see you guys. Okay. What's up? Tomorrow. I'm sorry.
Oh,
Tomorrow.
no, you're fine.
Just let me know again tomorrow, like, or Monday. I'll change the Monday. Listen. You can do it that way. Essentially what you can do here. Because this is what you're doing, right? Because now that's not what the front right? This is two ways of looking at it. I haven't got to fraction because I haven't. But it's the same thing. What I'll do now is we have a whole value, so I'll change this to this and do the x to the one third, right? Because I can separate them, and this becomes what? X to the one third. But if I want to write this as a fraction or a rational, right? So it's the same thing. If you like it that way, I'm going to show problems like that. I will show you guys. Okay. That's fine. That's fine. I think. Yeah. I just haven't done it yet. Awesome. That's what the video is.
Oh, look at it. It's sleeping. Oh, yeah. No, it's kind of tiny, Dad. I I'm done. Everyone be saying something ugly. I'm like, no, I'm done. Plastic surgery. Don't worry. No, she's not allowed to use it now. I don't know. It's just, today. Which dance? Which dance are you
Why did you make me write them down? Yeah, you did. You're like, all right, write them down. Don't even lie. No, I said, could you do them? Because I didn't. It's okay. I have a sub. And
I'll just come to you. Yeah. I know.
Oh, it's funny. Yes, watch out for me.
Tell me never.
Number two. Make it like this. Number two.